welcome to the third and already final day of the Nexperia Power Live event, and welcome back to our studio.
My name is Robbie Fernandez. I'm the Global Head of Marketing at Nexperia.
And I'm Petra Beekmans, Global Head of Communications at Nexperia. We hope you enjoyed the sessions yesterday on our automotive channel. Let's get started now with our GaN channel.
Here, live with you, are Scott and Giuliano to discuss how to overcome challenges in paralleling GaN FETs and increase the power capability of a power design. The session will take about 25 minutes. First a presentation and then questions. Questions are anonymous and you can ask your question using the question pane on the right-hand side of your screen. So please go ahead and ask your question to one of our experts or share your own experience and insights. And with that, I will hand over to Scott and Giuliano to begin. Gentlemen, please take it away.
Thank you, Petra and Robbie. Hello and welcome. In this session today, we're going to be focusing on paralleling Nexperia GaN FETs, and specifically how to overcome some of those challenges that present. My name is Scott Durkin, and I'm a Senior GaN Applications Engineer based in Manchester in the United Kingdom.
Hello everyone, I'm Giuliano Cassatro and I'm responsible for the GaN marketing and commercial activity. Today I'll be taking care of your questions related to commercial topics. Thanks for now, over to you, Scott.
Thank you very much, Giuliano. So today we're going to be presenting one practical implementation where Nexperia Cascode GaN FETs in the TO247 package have been paralleled successfully, and also talk about our recommendations and provide some tips for the designer. So here is shown the functional block diagram that has been implemented for the design. So the system has been realized on two PCBs with the interface between the two shown as the dashed line. On the left side here, we have the driver PCB, on which is the separate high and low side gate drivers, the dead time generation for shoot-through protection, the power supply for these circuits, which is not shown, along with the control signal and the low voltage power supply inputs. On the right side, we have the power PCB, on which we have the 4-off GaN 041 650 WSB devices, with two devices in parallel for the high side and low side in a half-bridge configuration, along with the power inductor here, the bulk decoupling capacitors here and here, the DC link snubbers, which are not shown in this diagram, and the high voltage inputs and outputs. As noted on the diagram here and here, the system can be either configured in buck or boost modes. And next, I'll go through the Nexperia recommendations and also show how they have been put into practice in this implementation. So the first recommendation really is that symmetrical placement of components, tracking and gate loops really is key to successfully paralleling Nexperia GaN FETs. And the reason for this is that so the effective impedance paths are matched as much as possible between all devices. With all of these in combination, any differences in gate drive signals in terms of voltage level or timing, for example, will be minimized, which leads to all the devices being switched on or off at the same time so that the current is shared equally. Let's now have a look at how this has been implemented practically in the system. Firstly, we'll look at the power PCB. So the image on the left is the schematic portion showing the paralleled TO247 GaN FETs, and you should see them, the four devices here. The image on the right shows the complete power PCB outline, and the image in the center shows the zoomed in area identified by the box. The devices on the left side, identified as Q2 and Q4, are the low side devices, and the devices on the right-hand side, identified as Q1 and Q3, are the high-side devices. So the image on the left, I've highlighted the nodes of interest, and the top one being the high voltage connection, and this one here being the switch node. And the point to note here, and has been highlighted in this image in the center, is that the copper plane for the drain connections of the GaN FETs, which are these connections here, 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 and here, have been made symmetrically as shown. This is because we want to have the current flowing equally and as balanced as much as possible between the devices. Next, we're going to look at the driver PCB. So on the left-hand side, we have the top layer of the driver PCB. On the right-hand side, we have the lower side of the PCB. And in the center, we have the schematic. And what has been highlighted here, again, is that the gate drives are all symmetrical. And we can see those highlighted here. So we have the driver chip here. These are the series gate resistors. And here's one of the tracks going off to the gate drive. This one being for the high side. This one here is for the low side. And if we look over on the other side, we can see the same again for the low side and this one for the high side. But if we just take a moment to look at the schematic, what we actually see is that although the driver board can accept gate resistors for each device, what is actually we've seen we can do is just have one gate resistor, which is common to driving both GaN FETs. One also thing to look at is the multiple vias in the source connections back to the driver. And again, this is done symmetrically. And we'll say that many times during this presentation, that symmetry is the key factor. So the next recommendation that we have is that RC snubbers are required to damp any resonance on the DC bus, and they must be placed as close as possible to each GaN FET. The reason for the DC snubbers is because of the resonance that you may get because of the from the DC bus. And this can lead to potential instability in the system. So here we have the bottom layer of the PCB. And in the zoomed image we have here, I've highlighted both the DC link snubbers, and there's 3 of those. So there's these components here at the top, there's one in the center, and one here at the bottom. And not only that, the decouplers for the high voltage have been evenly distributed across the devices. For our implementation, we've used 10 ohm resistors, shown here, in series with 10 nanofarad capacitors. For the final application, in your case, they will probably need to be changed and optimized for this. So the next recommendation we have is that the switch node should be as compact as possible. This is so that the inductance in series with the parallel devices and also the capacitance to other planes on the PCB is reduced as much as possible, which again could lead to potential instability in the system. So here we show the inner layers of the power PCB. And again, it can clearly be seen that the design of the switch node, which is this copper plane here and here, has been made as compact as possible, which is another aid to switching stability and reducing the risk of sustained oscillation. The rest of the copper on each layer is either used for the power ground plane or the high voltage plane, again, to reduce the inductance, as would be the normal practice in any high power design utilizing a multi-layer PCB. So here is shown the inner layers of the driver PCB. And again, the design of the switch node, which is here and here, has been made as compact as possible. And what we're trying to achieve is a very tight gate source loop as much as possible. And again, you can see here for the source connection that we've had multiple vias so that we have as little inductance as possible. The next recommendation we have is that provision should always be made in the design for switch node stubbers. We can also see here that the placement of the snubbers, which are highlighted here, so these are the snubbers for the low sides, and these are the snubbers for the high sides, are as close as possible to the pin on the GaN FET. However, these may not actually need to be populated. And I'll show later on that in our design, they were actually not required for stable switching. Another recommendation, each GaN FET must have a separate ferrite bead to damp the gate source loop. And the component that's been found to be extremely effective in damping the gate source loop and is recommended when utilizing the GaN 041650 WSB devices is shown on screen here. We can also see here that the gate ferrites, highlighted here in the circles, are as close as possible to the pins of the GaN FETs. So again, we want to keep that gate source loop tight as compact as possible. So the next recommendation is that drivers should be physically close to the GaN FET itself. This is again, we want to keep that gate source loop as compact as possible. However, if they are located on a separate PCB due to design, placement, or packaging constraints, then short, wide tracks, or ideally multiple planes, in association with large gauge terminals soldered between the boards is advised. This will reduce the inductance in the gate source loop as much as practically possible. The use of non-soldered connectors, such as plugs and sockets, are not recommended in the gate source loop, as they typically increase the inductance, and that does lead to an increased risk of oscillation. And that was actually seen during the validation tests that I performed in our lab. And the final recommendation, and would be the case with any other active power devices in a parallel configuration, the GaN FETs should be thermally very well connected to each other so that the temperatures are equalized as much as possible, leading to distribution of current equally. Now I'm going to share some results from the validation tests that were conducted in our lab. So the first test performed was a single shot 7-pull staircase test at 100 kilohertz. So for this test, we had a 50 microhenry inductor, which was connected to the bus voltage set at 400 volts, and the current flowed through the low side GaN FETs and then recirculated through the high side GaN FETs. Each applied pulse was 1.9 microseconds wide, which led to a peak inductor current of 114 amps. In the left image are all the captured waveforms from the test, and in the right image is a zoom of the last pulse. As noted, the yellow and blue traces are the low side gate signals. These were used for triggering. The magenta trace is the inductor current, and the green trace is the switch node voltage. If we look at the zoom of the last pulse, there's a few things to note here. Firstly, looking at the gate signals themselves, you'll notice they are very, very similar to each other. And that is one of the benefits of having the Casco configuration that we use. Also, it can be seen that as the devices switch off, that the oscillation on the gate is damped effectively, and as such, there's no risk of sustained oscillation in the system. If we also look at the voltage on the switch node, both the overshoot is nicely controlled and damped effectively during the switching events. Here we have the zoom of the last pulse again. But as noticed for these traces, again, the yellow channel has been used for the trigger from one of the low side GaN FETs. The blue trace is this time the switch node voltage, and the magenta and green traces are the device currents. If we look specifically at the magenta and green traces, we can see that the current is being nicely shared between the parallel devices all the way up to the maximum current here, where the devices get switched off. So here we have some captured waveforms when the system was being run in buck mode, with an input voltage of 400 volts, an output voltage of 225 volts at an output power of 6.6 kilowatts and a switching frequency of 100 kilohertz. Again, the yellow trace is used as the trigger, and the blue trace is the switch node voltage, and the magenta and green traces are the device currents. The currents are in this image here on the left are the high side currents, and these on the right are the low side currents. And as we can see, the currents are being nicely shared and nicely matched to each other. So we can see that the current is being shared equally between both devices. If we again looking at the voltage on the switch node here, both the overshoot and this one here, both the overshoot and undershoot is nicely controlled and damped effectively during the switching events. Here we have the results from the system running in boost mode, this time with an input voltage of 225 volts, an output voltage of 400 volts at an output power of 6.6 kilowatts, and again, a frequency of 100 kilohertz. This time, we can see again that the switch node voltage is nicely damped in this configuration and mode, very nicely at both switch on and switch off. And again, the currents are being nicely shared between the low side on this side, sorry, the high side on this side and the low side on this side. For further information on this topic, please visit nexperia.com, /GaN FETs, where you'll find the application note AN 90030 for this topic, along with the device datasheets and further resources. That concludes this section of the session, and now I'll open it up to the floor for any questions and insights that you may have.
All right. Thank you very much. Great session to start with, guys. We actually do have a question coming in already related to what was mentioned on slide 3. Is the bridge shorted?
I go back to slide 3.
Yeah.
Sorry, the question is the
bridge shorted.
So when we do the staircase test, we have the inductor shorted to a grounded. So that's the only time that we do.
Okay. Then we have the next question. Can devices with different date codes or batches be paralleled?
Yes, they can. Obviously, when you have a parallel configuration, there's a possibility that you may get devices from different batches. It's not possible that you can always get your devices same batch. Even within the manufacturing process, you're going to have different wafers and so on. And what we've actually done as part of this experiment is take devices with different date codes and put those together in this system. We found that there was no detectable difference in waveforms or performance. They were pretty much the same. Waveforms were nice, so no issues at all.
Okay, thanks for that answer. With a parallel connection of, for example, 4 GaN, is it difficult to keep the gate path symmetrical for all of them?
We're actually working on a system at the moment where we have more than the 2 devices, and really it isn't. I mean, generally in a system you'd be having this on a multi-layer board, and that gives you plenty of scope on those different layers to put your tracking and to keep them symmetrical.
Okay. Thank you, Scott. Then another question here. What method did you use to measure the drain currents?
So for that, we used Rogowski coils, and they were mounted around the device drain legs.
All right. Next one. How are the currents in high side and low side parallel FETs probed and measured?
So I think that's similar to the question that's just been asked. It is that we used Rogowski coils to do that measurement.
All right. Do we have time for one more question, I think? Okay. Is it needed to screen GaN FET parameters, for example, threshold voltage and artisan, to get a good current sharing between paralleled GaN FETs?
So that's similar again to the question before. And basically, in our manufacturing process, we have very tight controls on in terms of the threshold voltage of the low voltage MOS that's inside our cascode configuration. And that is probably one of the benefits of having the cascode configuration in the way that we have, in that we have a very tight control on the gate threshold voltage.
Good. Thanks for your answers. And actually that brings us to the end of this live session. Thank you, Scott and Giuliano. If you want to know more about GaN FETs, you can follow the resource links underneath the screen or chat to one of our power experts.
Please stay around. Our next live session on new CCPAC double pulse evaluation boards will start after a short break.